back in lecture series on chemical thermodynamics, and today we will derive expression for maximum work. In last video we have studied maximum work, concept of maximum work, and maximum work is obtained when there is a very small difference, that is infinitesimal small difference in driving force, that is a pressure of the gas, and opposing force, that is external pressure. And such a process in which a driving force and opposing difference between driving force and opposing force is very small, that is infinitesimally small, then such a process is known as a reversible process. And this reversible process takes place in large number of steps, that is infinite number of steps, and at every step equilibrium is attained. And therefore it is a very slow process. All these points we have studied in concept of maximum work as well as in reversible process. So today we will derive expression for maximum work. So let us derive expression for maximum work. For that, consider here a cylinder, and this cylinder is fitted with a weightless movable piston, and this gas, that is ideal gas, n moles of an ideal gas are enclosed in this cylinder, and pressure of this gas is P, which is called as a driving force, and the pressure outside this piston is P external, that is called as opposing force, and V1 is the initial volume of the gas. Now this gas is expand isothermally and reversibly. Isothermally means temperature of the system remain constant. So gas expand isothermally, and reversibly from initial volume V1 to final volume V2. And here as the gas expands, this piston, it pushes this piston in upward direction, and therefore displacement of this piston takes place through distance d, and volume of the gas therefore increases from volume V1 to final volume V2. Now as this change is carried out reversibly, the gas expand in number of steps. This change is carried out in number of steps, and at every step external pressure is reduced, that is opposing force. External pressure means opposing force is reduced by infinitesimally small amount than the pressure of the gas, that is P. And this gas therefore expand very slowly. At every step the change is very small and equilibrium is attained. Therefore gas expands slowly and its pressure decreases, and this expansion of gas continues, that is until the pressure of the gas equals to P external, and when this P external is equal to pressure of the gas, then expansion stops. So beyond this no further expansion takes place, and at that point system attains mechanical equilibrium with its surrounding. So like this change is carried out in a reversible manner, that is gas expands isothermally and reversibly. So let us understand this by this slide. See here, a gas, ideal gas is there in this cylinder, and here the 4 weights, that is 4 grams of a mass, if we put on this piston, then this mass on this piston that is exactly equal to pressure of the gas inside this cylinder. And suppose V1 is the initial volume of the gas, and this gas expands from initial volume V1 to V2. This change we have to carry out, but this change is carried out in number of steps. Gas in maximum, to obtain maximum work, the gas expand isothermally and reversibly. So if this change from initial volume to final volume V2 is carried out in number of steps, then what happens? How work is done, that we will see, and how the volume changes, that we will see. Suppose here these if you put 4 grams of mass on this, and if you remove 1 gram from this piston, then a small decrease in the external pressure takes place, and therefore small change or increase in volume also takes place, and volume in the increase in the volume is by dV. Very small change takes place, and V1 changes to Vx by removing 1 gram from this piston. Now again, this is the first step. In second step, if you remove again 1 gram from this piston, then this volume is Vx. V1 is increased by dV. Small change in volume takes place by dV, and V1 changes to Vx. Now this Vx, by removing 1 more gram, this Vx changes to Vy in second step, and again some small change in volume, that is increase in the volume, takes place by decreasing the external pressure by a very small amount. Now if this Vx, that is Vx, is changed to Vy, then in third step again this Vy, volume Vy, changes to volume Vz. Again if you remove 1 more gram, then again some small change in the volume takes place, and volume changes from Vy to Vz. Like this, if this change is continued, then at every step, every time some small mass is removed, that means small decrease in the pressure, external pressure takes place, so that small increase in the volume takes place. So like this change is carried out in number of steps. Now in this case, we have removed 1 gram. But if you increase this step by every time by removing 0.1 gram, then number of steps will increase. And at every stage, by removing 0.1 gram mass from this piston, every time very small work is done by the system. And when this mass or the force outside this piston becomes equal to the force inside this piston, that is pressure of the gas, when it becomes exactly equal to external pressure, then this moment of this piston will stop, and at every stage equilibrium is attained, because the change in the opposing force, that is pressure of the gas and pressure outside the gas, is very, very small. So at every step the equilibrium is attained, that is mechanical equilibrium is attained with its surrounding. Again from this equilibrium position, when you remove 1 more mass, 1 more gram, then again some small change takes place, again it attains what? Equilibrium. So at every state it attains what? Equilibrium with its surrounding. In such a manner, if this change is carried out, then that change is called as reversible change. So the volume of gas is increased by infinitesimal quantity, that is dV, at every time, in each step. In each single step, change in volume is dV, and every time some small change in pressure also takes place. External pressure is lowered at every time by a very small amount, that is by infinitesimal small amount. Like this the change is carried out. Then when the volume of the gas is increased by infinitesimal amount dV in a single step, then every time some small work is done by the system, and you know that you have studied pressure volume work and expression for pressure volume work. So according to the definition of pressure volume work, W is equal to P external into delta V. Whenever the change is carried out in an irreversible manner. But here the change is carried out in a reversible manner, and therefore work done in a single step is small work is done in a single step. Therefore dW, this small work is denoted by dW. So or work in a single step. That is dW is equal to minus P external into dV, where dV means what? A small change in the volume, that is dV. So dW is equal to minus P external into dV. So that is a change in that is work done in a single step. Now as this expansion is reversible, you know that pressure is greater than external pressure by a very small amount, and this small amount is dP, that is change in pressure, decrease in pressure is by a very small amount, and that is denoted by dP. Then the pressure of a gas, that is opposing force, driving force, minus external pressure, that is opposing force. That is, you know that pressure of the gas is slightly greater than external pressure. So this difference between pressure of the gas and external pressure is equal to how much? dP, that is very small. This dP is in very small quantity, that is infinitesimally small quantity, and therefore the P external is equal to how much? P minus dP. So if you substitute this value in this equation, above equation, this dW is equal to minus P external into dV. If you substitute the value of P external, then you get what? dW is equal to minus P minus dP, that is P external into dV, and that is equal to, combining this equation 1 and equation 2, you get what? This equation, that is equal to minus P dV, multiply this, open this bracket, so that you will get what? Minus P dV plus dP into dV. But dP is very small and dV is also very small. So product of this dP and dV, that is two very small quantities, is very small, and therefore dP into dV is very small. Hence neglecting this product, that is dP into dV, we get what? dW is equal to minus P dV. By neglecting dP into dV, we get what? dW is equal to minus P dV. So this is what? A work done in a single step. Here this change is carried out in number of steps, and every step small increase in the volume takes place. During the change, initial volume to final volume V2, V1 to V2, and this change is carried out in number of steps. Every time some increase in the volume takes place by very small amount, by decreasing the pressure by quantity, small quantity dP, and so that displacement of the piston takes place. That means work is done by the system on the surrounding, and every time small work is done by the system, that is equal to dW, and this dW is equal to what? Minus P dV, that is work done in a single step. Now if you want total work done in entire expansion of gas from initial volume V1 to V2, then you have to add all these work done during each step, that is dW terms. Sum of these dW terms will give you what? The total amount of work done during entire expansion of the gas. So if you add all these terms, then you will get what? The total work done. So to obtain the total work or to calculate the total work during the whole change, then we have to integrate this equation, that is dw is equal to minus p into dv between limits initial and final state, limits of initial and final state. So let us integrate this equation. So integrating the equation, dw is equal to minus p into dv, that is in between limits initial to final, that is equal to minus p dv in between limits v1 to v2. So here initial work is 0, at volume v1 work is equal to 0, therefore in between limits w is equal to 0, integration of dw in between limits w is equal to 0 to w is equal to maximum, total work is maximum. So w maximum is equal to minus integration of p dv in between limits v1 to v2. So here you know that in mass the integration of dx from limit x1 to x2 is equal to x1 to x2, that is x2 minus x1. So applying this to this equation, we will get what? Integration of dw between limits w is equal to 0 to w maximum is equal to w maximum, that is upper limit, minus lower limit, that is 0, and that is equal to w max. So integration of dw is equal to what? W max. So substituting that, you will get what? W max is equal to minus integration of p dv term in between limits v1 to v2. And you know that we have enclosed ideal gas, and therefore according to ideal gas equation, PV is equal to nRT. Therefore P is equal to nRT divided by V. So if you substitute this term in this equation, we get what? W max, that is maximum work, is equal to minus, we substitute the value of P, that is pressure. So P is equal to nRT upon V. So nRT upon V into dV in between limits V1 to V2. But you know that N means number of moles that are not changed, fixed. So N is number of moles, that is constant. R means gas constant, its value is also constant. And T means temperature. This process is isothermal. Therefore temperature of the system is also remain constant. So all these terms, that is number of moles, temperature and gas constant, all these are constant. So taking this out of the limit integration, we get what? W max is equal to minus nRT integration of dV by V in between limits V1 to V2. But in mass, you have studied this law, that is this formula, that is integration of dx by x in between limits x1 to x2 is equal to ln x x1 to x2. And applying that in this equation, we get what? W max is equal to minus nRT ln of V in between limits V1 to V2. And that is equal to W max is equal to minus nRT ln V2 upper limit minus ln V1, that is lower limit. So that is equal to what? W max, that is maximum work, is equal to minus nRT ln V2 upon V1. And that is equal to, here ln means log to the base E. ln means log to the base E. So here W max is equal to minus 2.303 nRT log to the base 10 V2 upon V1. Here the log to the base e. ln means log to the base e, and log to the base e is equal to this factor you have to multiply when it is converted log to the base e. When it is converted into log to the base 10, you have to multiply it by factor 2.303. So W max is equal to minus 2.303 nRT log to the base 10 V2 upon V1. So this is what the expression for maximum work. W max is equal to, note down it, W max is equal to 2.303 nRT log to the base 10 of V2 upon V1. So, but according to Boyle's law, at constant temperature, P1 V1, we have studied this in 11th standard, P1 V1 is equal to P2 V2, and therefore V2 upon V1, this term V2 upon V1 is equal to P1 upon P2. So if you substitute this value in this above equation, you get what? W max, that is maximum work, is equal to minus 2.303 nRT log to the base 10 P1 upon P2. Both these are the expression for the maximum work obtained in isothermal and reversible process, expansion process. So here question asks on this, that is, derive an expression for maximum work in isothermal reversible expansion of n moles of an ideal gas for 2 marks in state board exam. Or they may ask like this also, that is, derive an expression for maximum work in isothermal reversible expansion of 1 mole of an ideal gas. So if the question is asked like this, that is, derive an expression for maximum work in isothermal reversible expansion of 1 mole of an ideal gas, then instead of n you have to write 1. So the equation becomes what? This equation becomes W maximum is equal to minus 2.303. Instead of n there will be 1. So minus 2.303 RT log to the base 10 P1 upon P2. Or if volume is given, then W maximum is equal to minus 2.303. Instead of nRT, there will be only RT because n is equal to 1. So RT log to the base 10 V2 upon V1. Like this you have to derive an expression for maximum work. And generally this question is asked for 2 marks. So prepare it well and we will solve numerical problems based on this formula next time. Thank you.